All right. We finished up last class. Yeah, did I do example 5? I did, right? Okay. $13.4. Y'all ready? Green's theorem. This is a really big result in this class. Green's theorem. When you read the description for Cal 3 course, it usually says one of the main Green's and Stokes' theorem. So we are at Green's. We'll get to Stokes in 13.8. So what is Green's theorem? Well, before we can get into it, I'm going to have to make sure we understand a few things geometrically. But Green's theorem is a way that we connect the line integral around a simple closed curve to a double integral over the region bounded by the curve. So there is a curve C. It is a closed curve, right? Which means it comes back to itself, right? The initial point and end point are the same. And that curve C encloses a region D. The way you traverse this curve can be both clockwise or counterclockwise. The counterclockwise traversal of a curve is called positive orientation, right? Positive is counterclockwise. Just like with angles, positive was counterclockwise. Same thing with traversing a curve. All right, so there we have a positively oriented curve C that encloses a region D. So here's the theorem. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane. And let D be the region bounded by that closed curve. If P and Q have continuous partial derivatives on an open region that contains D, then here's the result. The line integral, now notice this little symbol, the little circle around here. That lets you know that your line integral, the curve C, it lets you know that it's closed. So by putting the circle around the integral, you let everyone know it's a closed curve, all right? A little bit more about that. If you have that little circle, it's assumed to be positive orientation. If you want to represent clockwise orientation, the other direction, then you have to put a little like arrow on the circle, the arrow showing clockwise instead of counterclockwise. So it's the way that you would let someone know you want to go the other direction around the curve, all right? So this says that if you want to do the line integral around this closed curve C with positive orientation of P dx plus Q dy. Now, I wanted to bring up last class because I wanted you to see something before I do the rest of that. Where is it? No, it was 13.2. This right here. Remember that line integrals can be broken up into these component integrals? Okay, just keep that in mind. So this is saying that this line integral of P dx plus Q dy turns out to be the double integral over D, the region it encloses, of partial Q with respect to X minus partial P with respect to Y with respect to area. So your line integral becomes a double integral. So let's take a look at this problem and work through it. So what I'd like for us to do is evaluate this line integral in two different ways. First, use line integrals. I mean, use a line integral to figure out what that answer is, and then use Green's theorem. Then we'll compare and we'll see which one was better. So I'm going to be doing the line integral over the closed positively oriented curve C, y dx minus x dy. And I'm doing this over the unit circle centered at the origin. That's my C. Am I positively oriented? Well, I need to go this way, right? So that means that I need to come up with the parametric curve, parametric representation of this. I could say R of t cosine t sine t. T is between 0 to pi, right? That'll give me one revolution. Now, to figure out these integrals, I'm going to need to know what dx is, right? I'm going to need to know what dy is, which dx is the derivative of x with respect to t, dt. dy is derivative of y with respect to t, dt. So let's go ahead and write those down over here. Dx is what? Negative sine t dt, right? Dy is cosine t dt. So this becomes integral from where to where? 0 to pi. Okay, we're doing the y first. What's y? Sine t. So we have sine t times dx, which is what we just found there, negative sine t dt. We're going to do that. And then we're going to have another integral, minus integral 0 to pi. I'm splitting it up into two. You could put it all together, right? You could do this all at one time. If I did it all at one time, though, I'd want to pull that dt out and just leave it till the end. What goes in here? X dy. So cosine t dt. Go with me? Okay, I'm going to factor a negative out of both. 0 to pi, I'm going to combine both together. Isn't that just sine squared t plus cosine squared t? dt. And that's just 1. Or just dt. And now I integrate with respect to t. So negative t evaluated from 0 to pi. Negative 2 pi. That wasn't too bad, right? Wasn't too bad? However, could we have used Green's theorem? Well, we have a closed curve, right? Positive orientation. Does it enclose a region D? Yeah, I could call this right here D, right? Do I have in my integral up here, do I have a P and a Q? Well, P, this is my P dx, and isn't this my Q dy? I have minus between them. What does the theorem have in it? Does it have minus or plus in the theorem? It has plus, right? So when I go back here, I can look at this as being, what, plus Q of X, Q right here? Yeah? So what's P in this problem? And what's Q? Negative X, right? So let me use Green's theorem instead. Using Green's, P is equal to Y, Q is equal to negative X, and according to Green's theorem, I can convert this line integral into a double integral over d of partial q with respect to x minus partial p with respect to y. So what's the partial of q with respect to x? So this is going to be double integral over d. Partial q with respect to x is -1 minus partial p with respect to y, right? Yes? So -1 dA. Oh, there's the call. Hold on. Yep. Give me just a second. Just hold on. So we have this, right? Did y'all finish it while I was in there? Too hard, huh? Okay, so what about our D? Our D is this, right? So we need to come up with this is just a double integral, right? We're doing a double integral of -2 dA, right? Over D. What type of region is this? It's a polar region, right? So I can convert to polar. So what's my restriction on theta? 0 to 2 pi. What's my restriction on r? 0 to 1. It was unit circle. So this double integral becomes integral from 0. I'm running out of room. I think I'm going to go to the next page. Y'all got that? Okay, so it's integral 0 to pi. What? 0, 1 of -2. I'll pull that out. D. Oh wait, r dr d theta. Almost forgot the r. Right? Because we went to polar. So now do the inner one, or you can do them separately, whichever way. I'm just going to do them separate, together. Antiderivative of r is 1/2 r squared. Evaluate 0 to 1. So what do we get there? 1/2. So now we're integrating 0 to 2 pi. We're integrating 1/2 d theta. We can pull the 1/2 out. So that's just negative theta integrating 0 to 2 pi. So you get -2 pi. Same answer, right? I think you would probably argue that maybe the other way was just as easy. I mean, I don't think that I would have convinced you with this one problem that, yeah, Green's theorem was really helpful, because the last one worked out pretty clean also, right? So maybe we should look at something a little more convincing, something like this. Look at this. So let's first just give ourselves some appreciation of what the line integral for this would look like. We have line integral over this closed curve, 3y minus e to the sine x dx plus 7x plus square root y to the 4th plus 1 dy. C is the unit circle, no, not unit circle, circle centered at the origin, radius 3, right? So if I were to try and come up with the parametric representation of that, I'd be looking at 3 cosine theta, 3 sine theta, or t, sorry, not theta. T 0 to 2 pi. Then I would need to find out what dx is and dy, right? Which would just be, what would dx be here? -3 sine t. Dy would be 3 cosine t. And now we would go plug everything in, right? And this is where things are going to get ugly, right? we would have integral from 0 to pi, and then 3y, which would be 3 times 3 sine t, right? So 9 sine t minus e to the sine of x, but what's x? What's x? 3 cosine t, right? All of that times dx, but dx was negative 3 sine t. I'll do dt at the very end of this. Then plus 7x, so 21 cosine t, plus the square root of y to the fourth, which would be what? 81 sine to the fourth t plus 1. All of that dy, which is 3 cosine t dt. And we look at this big monster, and we haven't gone there yet. Yeah. Just start throwing r's in all the time. When in doubt, add r to the integrand. So I don't think anyone here would be excited about integrating that, right? You'd be thinking Wolfram alpha at this point, wouldn't you? I mean, it could work, but it's just okay. So instead of doing this, right? Why don't we use Green's theorem? If we use Green's theorem, what's p? 3y minus e to the sine x. What's q? 7x plus square root y to the fourth plus 1. And then our double integral now our line integral becomes a double integral over d of partial q with respect to x. What's the partial of q with respect to x? 7 minus partial p with respect to y. 3 dA. So all we're doing is the double integral over d of 4 dA. That's all it's going to turn out to be, right? All we need to do now is come up with that region. That region is a polar region, isn't it? Theta is between 0 to pi. R is between 0 to 3. So this becomes double integral 0 to 2 pi, 0 to 3, 4r dr d theta. And I think you would agree that that looks pretty easy, right? I mean, relatively speaking, that's a lot easier to do. Okay? Do you want to do it or not? Yep, we'll just finish it off. We've come this far, right? 0 to 2 pi. Antiderivative 4r is 2r squared. Evaluating 0 to 3, d theta. So we plug in 3 squared, 9, 18, right? So we got 0 to 2 pi, 18 d theta, which is theta, 18 theta, evaluated 0 to 2 pi. So you get 36 pi. Questions? Take-home mini exam? You have that problem right there? Remember that problem on your take-home mini exam? Did I give you the direction of the curve? That can be done two ways, right? You can do the line integral, or you can apply Green's theorem, right? It's a little more challenging, though, because the curve is not a single curve, right? Look, you have two curves. So your region is actually two regions that it encloses, isn't it? So you'll have to think about how you might do that. It's not super complicated. It's just a little different than what I just did. All right, so we can see that sometimes computing the line integral over a closed curve is easier when we use Green's theorem and convert the problem to a double integral. There are other cases where we can convert double integrals to line integrals. So remember from double integrals that if you wanted to find the area of a region D, you do the double integral of 1, right? Remember that? All right, now remember that with Green's theorem, this piece in here, this 1, for Green's theorem was partial of q with respect to x minus partial p with respect to y, right? So if that thing in there, if the partial of q with respect to x minus partial p with respect to y is 1, then there's different ways that you could get that to happen. So I give us a couple of cases here. Let's say that your p function is 0 and your q function is x. Then what's the partial of q with respect to x? 1 minus the partial of p with respect to y would be 0, so you get 1, wouldn't you? So if p is 0 and q is x, then you will have the Green's theorem, that thing inside will be 1. Now you could do it this way also. If p was negative y and q was 0, then if you computed that partial q with respect to x minus partial p with respect to y, you would also get 1, right? So look, do y'all see that these are formulas that we're coming up with for areas? In this case, you get this line integral is the area of D. If you do it this way, this line integral is the area of D. And you could even do it, there's a bunch of different variations that you could try, but these are the common ones. If you let P and Q be those two, then that would represent your area. Does everyone understand that in each of those cases, by letting P and Q be those things, that when you do Green's theorem, you get 1 in the double integral? So we're going backwards. We're trying to get 1 in the double integral. These are 3 different ways you can get 1 inside the double integral. So take a look at this. Find the area of a circle radius r. We've done that already, right, with the double integral? If I have a circle, let's make it radius capital R. Okay? We all know it's pi r squared. We've done it with the double integral. How did we do that with the double integral? We said our theta is between 0 to pi. We said our radius is between 0 capital R. And then we did double integral, right? 0 to 2 pi, 0 to capital R, and what did we integrate? 1, but then we have to put the R for the polar conversion, dr d theta. We did that in class already, right? When we first were doing polar integrals, polar coordinates, sorry, and double integrals, we showed that we could come up with the area of a circle. And we were pretty impressed with that, maybe, that, oh yeah, that's pi r squared, great. But now what we're going to do is we're going to do the same problem. We're going to get pi r squared, but we're going to use a line integral instead of a double integral. So if I want to find the area of D, I can use any of those 3 formulas that I just had. I'm going to start with the first one. It's the line integral over C of, what was the first one we had? The first formula, x dy? X dy. Now, what is the C we're talking about here? D is this region inside here, right? C is the curve going around it. All right, so C is this. Yes? C. So you need to come up with a parametric representation for C. But we've done that so many times now, right? Radius of this was what? R, so isn't it R cosine T R sine t? What's going to be dy for me? R cosine t dt, right? So this integral becomes integral from, I didn't put my restrictions, but t was between where? 0 and 2 pi, right? So I'm going integral from 0 to pi of x. What's x? R cosine t. What's dy? R cosine t dt. Would you already agree with me that this is more complicated than just using the double integral? Okay, but it's just to show you it works. That's all this is, verification that we can go the other way with it. Okay, so what would we have here? Bring capital R squared out. 0 to pi. How would you integrate cosine squared t? Half angle, so it become 1/2 plus 1/2 cosine 2t, and then dt. So all we did there was use that cosine squared t is equal to 1/2 plus 1/2 cosine 2t. That's your power reducing formula or double angle. There's different ways of looking at this. I've seen it called different things. I've always called it the power reducing formula because it reduces the power on cosine. Integrate those term by term. What's the antiderivative of 1/2? 1/2 t. Antiderivative of 1/2 cosine 2t. 1/4 sine 2t. And we're going to evaluate that from 0 to 2 pi. All right, let's plug in 2 pi. Plug in 2 pi. Get 2 pi here, right? Cancels with the 2, so you just get pi. So r squared, you just get pi there. What happens when you plug 2 pi in right here? You get 4 pi and then 0. Sine of 4 pi is 0, so that's all 0. So we get plus 0 here. And then when you do the next one, what do you get when you plug 0 in? When you plug in 0, you get 0, so everything else goes away. So all you get is pi capital R squared. Same result. Questions? No? Okay, now let's appreciate the formula here. Or the whole idea of finding the area using a line integral. Find the area of the figure below. An epicycloid given by the parametric equations x equals 5 cosine t minus cosine 5t, blah, 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 blah. T is from 0 to 2 pi. So if I want to find the area enclosed by this, if I use a double integral, right? A double integral like we did with the circle just a second ago, I would need a way of defining these regions, right? Is this a polar region? No. Is it type 1? Is it type 2? See what I'm saying? You see the challenge here? It's not a polar region. It's not a type 1. It's not a type 2. It's something different, right? So instead of trying to figure out a way of defining this region, what we're going to do is we're going to say, look, there is a curve, a closed curve, right, that encloses that region. So instead of doing a double integral over D, we're going to do a line integral over C instead, and we'll be able to get the area inside. Understand? The question is, which of the three do you want to use? There were 3 different formulas. I really don't think it's really going to matter in this problem. We can do the one we just did, which was what? Line integral over C of x dy, right? That'll give you the area of that. Or you could do line integral over C of negative y dx, or you could do that third one, which is combination of both. So just for the sake of this example, why don't I use the second one so we can just see the second one being used, all right? This is C. Now, I kind of put the arrow there that it was positive orientation. We would have to check that to make it sure it is. How could we check that that's positive orientation, that it is drawing that curve counterclockwise? Plug in a couple of values. Okay, so what if t is 0? Where are we if t is 0? You have to plug it into the parametric equations. Four for x. How about for y? 0, right? So that works. Let's try something else. How about pi over 2? Where are we hoping we're going to be? Up at the top there? So let's see, if we plug in pi over 2, cosine of pi over 2 is 0, isn't it? What's cosine of 5 pi over 2? I'm plugging into this, right? Cosine of pi over 2 is 0. What's cosine of 5 pi over 2? It's still 0, right? So you get 0 for the x-coordinate. How about this? What's sine of pi over 2? 1. And then sine of 5 pi over 2? Y'all okay? This is pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Right? So it's 1. So we get, what's the point? Where are we? 0, 4? So we went from here to here. I think it's safe to assume that we did this, right? That we went that way. If we plug in more angles, it should turn out that we are, going to go around counterclockwise. Is that good enough? I'm not going to go through and plug more in. But okay, so we know this is positively oriented smooth curve, piecewise smooth curve. So let's go ahead and, oh, is it a smooth curve? It's not smooth at these corners, right? But if you look at the Green's theorem here, let C be a positively oriented piecewise smooth curve. What does piecewise smooth mean? You can, if you break it into pieces and on each piece it's smooth, then that's okay. So you can have little cusps as long as it can be broken up into pieces where each piece does not have a cusp. Just a little subtlety there I want to kind of pay attention to. All right, so now getting to the work here. I'm going to try and find the area of D by computing the line integral over this closed curve C of negative y dx, right? Now, the parametric equation, we already know what x and y are, don't we? I'll write it x and y instead of using the vector notation. X was 5 cosine t minus cosine 5t. The y was 5 sine t minus sine 5t. All right, we're going to need dx, aren't we? What's dx here? Negative 5 sine t plus 5 sine 5t dt. Y'all agree with that? So let me go and plug everything in up here. We're going to go integral from where to where? 0 to 2 pi. That was given, right, in the problem? And then the negative y, which for us will be negative 5. I'm going to just swap the order. And then we multiply that times negative 5 sine t plus 5 sine 5t dt. And we multiply this out. So here to here, we get negative 5 sine 5t sine t. Can't do anything to that, right? Can't put those signs together. Here to here, what's that? Plus 5 sine squared 5t. Okay, inner one here, what's that? Plus 25 sine, is it squared? T. And then finally, what? Minus 25 sine squared 5t. What? Oh, yeah, yeah. Thank you, thank you. I was looking at the wrong place, I think. Sine t, it's still negative 25 sine t sine 5t. dt. Yeah? Anything happen here? Anything clean up? First and last ones? That gives me how many of them? Negative 30 of those? Ooh. Negative 30 sine 5t sine t. Okay, the inner ones, they don't clean up, do they? All right, we're there. Now, could you integrate these? That's my question. How about the final two here? Could you integrate those two? How would you do these? It's 3 integrals, basically. You use the power reducing half angle, whatever, right? You could turn your sine squared and sine squared, you could break those down, so those would be okay. What about this one right here? Anyone know how to do this one? You might be able to do that by parts, but there's an easier way. There's a pre-cal formula. It's your product to sum to product formulas for trig functions. Who brings their cheat sheet with them? The ones that are, can I see that real quick? Let me see it. I'm sure it's there, but I'll tell you where exactly it is. Trig. They don't have it. No. Interesting. Well, yeah, there might be a formula for it in the trig stuff, but no, I don't see it there. That's weird that they don't have it on your trig summary. Well, it's got to be in the book somewhere. So let me look for it real quick. Although it actually may not be in the book. It'll be in your pre-cal book. You got it? Break that out, please. Let me steal this internet connection real quick. It's product of sum formulas. Oh yeah, it'll work. Product of sum trig. Let me see. When I bring it up here, maybe it'll look familiar. There we go. That look familiar? No? It's this is the one we'd be using right here. Sine, right? Because we have sine 5a, sine A, right? So this sine 5a, sine, no, we have t. Sine 5t, sine t, you would break it down into this. And that's just a cosine. A cosine, they're separated by subtraction. And then you just integrate each one of those. What do you think? Think you could do that? The moral of the story is that this integral, even though it may not look that great, is still a lot better than our other option. Because our other option was to try and find a way of defining that region D, which wasn't easy to do. Now, do you think had we used, I'm going to stop here. I'm going to say dot, 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 meaning you could finish that off. But do you think that if we would have used the other formula up here, x dy, it would have made it any easier? Well, what would x have been? This here? And dy would have been derivative of this. It would have been very similar to this one, wouldn't it have been? What about that third formula, though? Do you think that would have made a difference? What is that one? Do you think that one would have worked out better? Do you think some stuff would have canceled? You think some stuff would have canceled? It's worth a shot, right? Do you want to try it? I don't think I've tried it. You don't want to try it? No? Because look, I mean, as nice as the fact that we can do that integral doesn't mean it's necessarily the easiest one. See, the question would be, why would they even look at this formula here, right? Like, what's the use of this formula if it looks more complicated than those, right? Maybe in this example, this formula will actually make this problem easier. Okay, so I'm gonna do it, and if it turns out where it's going to look too ugly, and we won't do it, we'll stop. But I'm going to copy this whole page. No, I'll just copy the beginning here. Let's try it this way. Area of D equals line integral. What are we going to do over C? It's 1/2, -1/2, y dx plus 1/2 x dy. So all we really need, what? Yeah, y dx is what we had earlier, right? Let me see, let me go back to what we had. We'll have this with a bunch of sine, but imagine over here that I had a 25 cosine squared over here. If I would have had a 25 cosine squared over there, and added to that, wouldn't that have been a 1? You see what I'm saying? So I'm saying possibly, I'm not guaranteeing anything yet, but I'm just saying it could possibly work out. So do you all agree with this, though? This line right here, we have this line, right, with a 1/2 in front of it. That's this first one. That's this one right here, isn't it? That with the 1/2. And let's just pull the 1/2 out. That's what I was kind of getting at here. If we pull the 1/2 out, line integral over C of y dx, negative y dx, plus x dy. So what we need to find out right now is what's x dy. Can we go do that work right now? Okay, we already know what x was. What's dy? 5 cosine t minus 5 sine 5t. That's dy. I'm coming back to this. I'll be back up there in a second. I need to multiply that times x, right? Oh, yeah. Thank you, cosine. So x dy will be 5 cosine t minus cosine 5t times this 5 cosine t minus 5 cosine 5t. And what do we have there? 25 cosine squared t. Hey, that's a good thing, right? Right, because we did pull, oh, but it, yeah, okay, let's just keep going. That's this. Now, minus 25 cosine t cosine 5t. That okay with you? Yes? And then this one right here, which will be minus five cosine 5t cosine t, and then plus 5 cosine squared 5t. So we have 25 cosine squared t minus 30 cosine t cosine 5t plus 5 cosine squared 5t. All right, all of that is just this, right? That's this. And then from the previous page, it was this piece, actually right here, wasn't it? I'll grab it. I'm gonna grab it and bring it over. It was that right there. Okay, so this piece would be that right there. Do y'all agree? So we're going to add the two together. So when we add those together, what does this and this become? 25, right? So we'll have a 25. And then what about this and this together? It's a 5, isn't it? So we have plus 5. And then these two don't add together, do they? I mean, I can't put them together. Negative 30. But could I do negative 30, factor out, and then just do like sine 5t sine t plus cosine 5t cosine t? Could I do that? Are y'all with me on this or not? I know I'm kind of like all over the place, but yes, I see you, yes. This is 30 minus 30. What about this? Where are your other formulas? Break out your formula sheet. Product. Yeah. What is it? Double angle trig. That should be good. Let me see. Not double angle. I want. Yes. Addition angle trig. There they are. What do you know? It's on Wolfram Math World from Wolfram.com. Look at this right here. Do we have one of these right here? we have sine, sine, and cosine, cosine. Are they added between them? Is it this one right here? What's our beta and what's our alpha for us here? 5t and t. Does it matter which one we use here? So this all turns into what then? Cosine 4t. Right? Now that's more like it. We can integrate that, right? See what I'm saying? The second formula didn't really, I mean, we could have done it, but it would have been kind of ugly. This last one, things canceled, things got better, and we've got something that's very much, you know, in the realm of integrability, right? So I'm ready to do my final integral. I'm doing integral, right, from 0 to pi, right, of 30 minus 30 cosine 4t dt. That's all I have to do, right? Which is 30t minus 6 sine 5t. No, sine 4t. Oh, wait a minute. Hold on. Yeah? Is that right? 30 over 4. I don't know why I was thinking 30 over 4, right? 15 halves, whatever. Sine 4t, and then 0 to pi. Oh, wow. Look what's going to happen. 2 pi. When you plug in 2 pi or 0 into this, right, it's going to be 0. So all you're going to get is what? 30 times 2 pi, which is 60 pi. Had anyone tried the other one on the you didn't do that other one on the calculator, did you? This one right here that I said dot dot dot. You didn't do that one. Okay. Yeah, is there 1/2 in there still? Yeah, thank you for bringing that up. I don't think we put that 1/2 back in, did we? Yeah, the 1/2 came out. Oh, right there. Yes, that 1/2. So that 1/2 is going to come down. So this integral, put that 1/2 out here. Thank you for pointing that out, Evan. So half of that whole thing, 30? 30 pi? All right. Now, let's do something here. What I'm going to do is I'm going to bring up that ugly one we had. This one right here, right? Okay, someone have that written down? I'm going to put this into Wolfram Alpha. See if we get 30 pi. Okay, so we're doing integrate negative 30 times sine. Yes, I did. Sine 5t sine t. Plus 5 sine squared 5t. What else? Plus 25 sine squared t. Okay. That's it? That's it? Yeah, I'm going to put that, okay, from 0 to 2 pi. See what happens. $30 pi. glad that worked. I don't think I've done it that way before, so it makes me feel better that worked out. Yeah? Okay. That at least gives you some appreciation for that third formula, because most of the time we avoid it because it's more complicated. But in some scenarios, it actually works out better. All right, back to business. All right, find the area of the circle. We did that. Find the area of this epicycloid. Did that. Okay, example, Green's theorem. Find f dot dr given this vector field, where C is the triangle from 0, 0, 2, 6, 2, 0, 0, 0, 0. All right, let's go for this. So we're trying to find this line integral over a vector field, right? What is the line integral over a vector field? Another way of interpreting that is as what? Line integral over vector. FDR is gradient, yes. I'm saying, what does that give us? Like in a physical representation that when I first introduced FDR, physically, it was the work, right? It was work. That's how we had that's how we had geometrically tried to understand what FDR was. So this is like a work problem. We're trying to compute the work done when you take a curve that connects 3 points of a triangle. 0, 0, it goes to 2, 6, and then 2, 0, and then back. I'm also given my vector field. Right? My vector field. I'd like for you to kind of tell me what you think you want to do here. We're trying to find the work done. We're given this path C. What's your instinct here tell you? Yeah, so you're seeing that that's clockwise, not counterclockwise. So we couldn't use Green's theorem directly because it has to go. So yes, we would reverse the direction, which would change the sign to a negative. Yes. But are you thinking Green's theorem? Are you thinking just do this like a regular line integral way? What are you thinking here? What's that? Or potential function? Could you use the idea of a potential function here? What would work best? How about this one? If we're trying to compute line integral over C, this is a gradient vector field, but it's a vector field .dr. Then we can just evaluate at the endpoints, right? But what about this curve that we have? What's the starting point and the end point? Same point. So it could be 0, right? The answer could be 0 with no work at all. However, what would we have to show in order to use this? That it's a conservative vector field. How do we show that something is a conservative vector field? This right here, right? Now check this shit out. I'm sorry, I had to use that language. What is, does this look familiar now? Move the partial p with respect to y to the other side. Right? If you did that, then they're equal, right? Then what would it be? It would be partial q with respect minus partial p with respect to y would be equal to what? 0. And then your line integral would be 0 of 0, which should give you 0. Do you see what I'm saying? That's why this condition is what you need for conservative vector field. But anyway, let's check this. Is the vector field that we're given conservative? Did y'all just catch what I just said? That was kind of a big point that I made there. So is it conservative? We're calling this P, we're calling this Q. What's the partial Q with respect to X? Ooh. What's the partial Q with respect to X? So 2X plus 2Y cosine X. This is not looking good. What's the partial P with respect to Y? 2Y cosine X? Agreed? What does that tell you? This is not a conservative vector field. So, important thing here. You would not go trying to find the potential function. Why? It's not going to exist. Now, we've never tried to find a potential function of something that doesn't have one, but I'd imagine there's got to be some problems in there, right? I mean, there's got to be an issue somehow in there. Is it something that we want to visit or no? I mean, do you want to go try and find a potential function even though we know it doesn't exist to see what kind of hang up you run into? Or do you want to trust that you'll remember to always check this first? You're going to trust that you're going to check that? Okay. So, back to this problem. Big picture. We look at it, FDR. First thing I'm thinking is fundamental theorem of line integrals. Is my F conservative? If it is, I'm pretty much done and the answer is 0, right? But I check the vector field. It's not conservative. Since it's not conservative, now I start thinking, well, I can either find parametric representations for each portion of the curve, right? I break it into C1, C2, C3, find the parametric curves for each one, and then compute f.dr for that, right? Which would take quite a bit of work, quite a bit of time. Or I can convert it over to a double integral over D, where D is this region. It's a triangle. Come on. I mean, that's the best type of region we could have, right? Type 1? Yes? So I think after all that process of thinking there, the best thing would be to go for Green's theorem here, right? Okay. So what I'd like to do here is just make sure I reestablish here F is not conservative, okay? Therefore, fundamental theorem line integrals does not apply. I sure wish it had. Now, to do Green's theorem, we need to have a positively oriented curve, don't we? Well, that's not positively oriented, so I'm going to come in here and I'm going to call C negative C, right? Negative C is the curve that goes the other way, isn't it? So here's what I can say using Green's theorem. And let me label D inside here. Green's theorem, I'm going to start a new page. Green says that the line integral over the closed positively oriented curve for us, which is what? Negative C, right? Of what? F dot dr will be equal to the double integral over D of partial Q with respect to X minus partial P with respect to Y dA. We'll go back and look at these integral properties to see how we're going to deal with the negative c in a little while. But that's what the theorem tells us, right? Negative c is a positively oriented curve. All right, let's do our partials we already did, right? What about our region? Let's get our region right now. Type 1 region. What's the restriction on x? 0, 2. Restriction on y? 0 to, what was 6x? 6x, right? Slope of that line, was it? 3x, right? Careful here, right? This is the point 60. I mean, yeah, 2, 6. What the hell? So the slope of this line is 3, not 6, right? Everyone follow that? Type 1 region. So my double integral becomes, notice I'm not going polar or anything like that. Partial q with respect to x. That was that one. It was 2x plus 2y cosine x, right? Minus partial p with respect to y. 2y, are you kidding me? Cosine x, is that really what it is? dy dx, are those really going to cancel each other out? That's good news for us, isn't it? Integral 0 to 2, 0 to 3x of 2x dy dx. We integrate that with respect to y first. We get 2xy 0 to 3x. Replacing what with the 0 and what with the 3x? Y. So when we replace y with 3x, we get 6x squared. When we replace y with 0, we get 0. So we're integrating 6x squared. Antiderivative of that. 2x cubed. 0 to 2. 16. I dare you to do it like a normal line integral. I mean, I dare you to torture yourself. The Green's theorem is extremely nice here. Okay, now, that's what we got, 16. The question is, we had changed the orientation in the beginning, right? Does that change our answer? Let me go back to, see in your notes here, probably be easier for me to find it. In the previous section, 13.3, did I give you any of the properties for signs of these things? I had to have. I didn't. Thought I had. I thought I had. Okay, let me reference you to a page then. Did that all make sense, though, as far as the setup of that? Okay, the bottom of page 769. The bottom of page 769. I'll throw it here in the corner it says there you go. That's a negative sign out front. It's negative. So if you change the orientation of the curve, the direction of the curve, it changes the value of the line integral over the vector field. So for us, by changing the orientation to make Green's theorem work, we have to now go back and change the answer to negative 16 instead of positive 16. Okay? So I'm going to scrap this, and I'm going to say, well, I'll keep that. I'll just put this one. Right. This is what we got, right? We got this. And that came out to be 16, right? We change the sign, and that changes the orientation to positive. So it comes out to be negative 16. That make sense? Let's change it. Did I put it on there? Hold on. That's with respect to x, y, and arc length. So I thought I had put that. That was for line integrals over scalar functions, not vector fields. All right, we're still in Green's theorem, right? How are we doing on time? All right, good. Y'all hanging in there? Do y'all have this in your notes? Lucky me, I've got it, you don't. I don't think there's much here. Yeah, it's only two things. So you just have to kind of pay attention here. All right, consider a region D containing a hole in it as shown here. Consider two paths, C1 and C2. These paths are chosen such that when you traverse either path, the region D is always to the left of the curve. So you got that region, right? The D is this region with this hole cut out of it. We create these two paths, C1 and C2, so that when you go along the path, the region that we're talking about is to the left of you, right? So C1 is counterclockwise, which is positive orientation, right? C2, as I move clockwise, the region is to my left. With me? Yes? Now, split D into two regions as shown below, D1 and D2. Right? D1 and D2. So what I'm going to do is somewhere on this path C2, pick a point, make go across over here, and then over here, pick a point and go across here. Y'all got that? Yes? Notice the two new paths, E1 and E2. So we had two paths, C1 and C2 before, right? Now I want you to see two different paths. E1, which starts here, positive orientation, goes around like this, comes back, goes like that, right? That's E1. E2, we'll say, starts here and goes this way. That has positive orientation also, right? Yes? Also notice the sections shown below the paths are in opposite directions, right? So this part, I had the green path went this way and the yellow path went this way. And so those two are going to cancel out, those parts, right? Do y'all follow that? Back up to this picture. If you go across the green here, whatever the line integral is just from here to here, right? That line integral, whatever it is, should cancel out from this line integral because they're in opposite directions. Yes? if we add them all together. Therefore, the double integral over d, okay, d was the part with the hole stuck out of it, right? Pulled out of it. That's Green's theorem, right? This double integral was the d1 and the d2 put together, yes? But by the fundamental theorem of line integrals, it should be the line integral of C1 plus the line integral of C2. Why? D1 was this whole path, right? Sorry, C1 was the whole path, right? Why is it just the C1 and C2 added together? It's not as obvious as it looks. That's why I'm trying to get you to... The cancel out part was pretty, I hope, obvious, but why is it that the double integral over D1 plus the double integral over D2 is just these two paths, the line integral on those two paths? What's that? No, I'm not saying you're wrong. If we went the opposite direction on C2, look, this is the part that's subtle. Look, let you look at those paths again. Those two paths, right? Look at this. When you go around D1, okay? When you go down, C1, remember, goes all the way around, right? But when you go around D1, you're going positive orientation, right? But look at the way that you go across C2. Which way are you oriented? Negative orientation, right? Across this part of C2. And then when you come over here on E2, it's positive, right? But when you get to C2, what is it? What's your orientation on C2? Negative orientation? And then you go across like this. Why is it that when we put those two integrals together, so look, C1, C1 would be this, right? All the way, like this. That would be C1 positive orientation. What would C2 positive orientation be? Positive orientation. It would be the other way, like this, right? Why is it that when I add those two together, I get the same thing as the double integral over those regions? I think I'm going to have to draw it on the side. I'm not sure. That's not. Uh-huh. And so when you subtract it and it's already going different orientation, it means add? Is that what you're getting at, or no? It's a negative integral because it's negative C. But we have two ways of doing this right now. We can just take this on faith, or we can see it from the geometry of what's happening. So what do y'all want to do? Because I want to convince you by you being convinced, not just take it on faith. So if you don't see why this is this, then I think we should talk about it a little more. Yes? Okay. Let's start back up. E1, E2. What does the E1 integral, line integral, give us? Use the Green's theorem with the E1, and what would you get? I think I'll write this on the board. So Green's theorem on E1 says the line integral over the closed curve positive orientation of E1, right? And I'm just going to put in here that partial stuff, right? I'm not going to write it down. Is equal to double integral over what? E1 closes off what region? D1? No, this was the partial stuff, dA. Got that? Do y'all agree with that? Okay, so now what about the line integral over E2? Well, E2 is also positive orientation, right? So doesn't that give us double integral D2 dA, right? Why is it that when we add these two together, it's the same as the line integral over C1 and C2? Because that's what the formula says, C1, C. Does everyone see E1, E2 from the picture? Yes? Why is it that the E1 and E2 added together is the same as C1 and C2? Well, C1's a curve, so you can't talk about area. Well, I mean the area. So when you add the area to C1 and D2, you get the area to C1 minus the area to C2, right? And by area, I mean the area, the region surrounding by the curve. Let me try and go around C1, okay? Let me try and go around C1 right here. Okay, I'm on E1, right? I'm on E1? Okay, if I keep going, am I on E1 anymore? No. I'm on E2, right? Hold on. Let me keep going, okay? So I'm here, right? If I keep going now, right? That gives me C2. I mean, that gives me C1, but I'm not on E1 anymore, right? I'm trying to figure out why it is, or trying to help you convince you from the picture that when you put E1 and E2 together, it's the same as traversing C1 and C2. Well, they both cover C1 and C2, and the areas where they grid them are in opposite directions, so they cancel. And then the areas where they cover C2 are in agreement because they're both negative, and then the areas over C1 are both positive. I think I agree with you. Hold on, let me get a different color up here, though. All right, so this part here, right, that's part of E1. And then if I want to go the rest of the way, right, I need that piece right there. That would give me C1. Yes? Then if I want to do C2, I'm going to do this part here, right? And then I'm going to do this part here. Now these parts are a wash, right? These are going to cancel out when you go in opposite directions. But what about orientation? Which way are we oriented here with C2? Yeah, but the orientation here is clockwise, right? This one, C1's fine, right? C1 would be Green's theorem, no problem. But E2, we go this way, right? Don't we? E2, we go this way. It's not a question. It's a does. Are you convinced that? Are you convinced that the double integral? Are you convinced of this relationship right here? Are you convinced that the two double integrals over those two regions, D1 and D2, are equivalent to the line integral over the C1 and C2? That's the question, of whether or not you're convinced of that. Now, I was trying to save myself time by not having to go through this, but let me tell you how you could do it. And, you know, the book might even do it for you, too, so let me see if they have it. But you could just break up the line integral on each of those pieces. On each of those pieces, just go from here to here, call that something, then this something, right? And then call that something and this something, and then put them all together, and you'll get things to cancel, and you'd see that you'd be left with the C1 and C2. It's an algebraically you could do it. Now let me see if they do it in here or not. I know they do. Yes, they do. This is on page 786, right in the middle. Page 786. So what I recommend is, if you want to look at it, they break it down a little bit. They don't show you as much of the geometry of it, but you can do it algebraically to show that this is true, right? So check this one out. Show that this line integral, or the work done by this vector field over this curve, is 2 pi, given this, where C is any closed path containing the origin. This is a look at our C. That's a pretty crazy concept here, but this is a nice result of what we just saw. Y'all write that down, because I know you don't have that, right? Y'all got it? Now remember this, what we just said here. This is what we said, right? We have this curve and we got a hole in it. Then at the very end of it all, that the line integral over C1 plus line integral over C2 is equal to the double integral over D of these partials, right? That's what we've got? Okay, so we're going to go now and try and work this one out. I think I have that one right. Y'all ready for a break or what? Yeah? Y'all want to do a break now and then come back and do this one? Okay, let's just do a quick 5-6 minute break. Okay, so we're trying to show this. I'm gonna write this down. We're trying to show that the line integral of the closed curve C of f dot dr is equal to 2 pi, where f is negative y over x squared plus y squared, x over x squared plus y squared, where C is any closed path that includes the origin, encloses the origin. So that means that my path can be any path as long as it's closed. Doesn't matter what it looks like, as long as the origin is inside there. All right? There's no way to check every path, right? There's just absolutely no way. So here's what we're going to do instead. And this is very tricky. Probably you wouldn't have thought of this on your own, which is why we show it to you. What we're going to do is we're going to call this C, right? And let's give C positive orientation, right? And then we're going to pick another path. This other path inside is going to enclose the origin. Call this C prime. Give it positive orientation, like that. And here's what I want to say about C prime. C prime is going to be R of t equals A cosine t, A sine t. T is between 0 and 2 pi. And A is a positive number. So this C here is a circle radius A, isn't it? I'm sorry, the C prime is a circle radius A. That's centered at the origin. So that little C prime should also include the origin in it also, right? Okay. Now, what I've done is I've created a region D, which is the region between them, right? The region between them. So do you see the similarities between that picture and this one right here, right? Except in my picture, both curves are positively oriented, right? This one here was negatively oriented, right? And the result of this was that the double integral over D of partial Q with respect to X minus partial P with respect to Y with respect to area was equal to the sum of the line integrals on those paths, right? But remember, the C2 was what? Orientation was, in this one, it was negative orientation, right? In ours, it's positive, isn't it? So for us, it'll be what? Line integral over C, right? And then minus line integral over C prime, right? The negative, because our path is positively oriented. So here's what we can write. Therefore, the line integral over C, and it's closed, of f dot dr minus the line integral C prime of f dot dr should be equal to what? Should be equal to what? The double integral, right? The double integral of D, right? Partial Q with respect to X. What's the partial of Q with respect to X? So here's P, here's Q, right? What's the partial of Q with respect to X? Well, shit, that's going to take some work, isn't it? What's the partial of Q with respect to X? Little quotient rule there, right? Derivative of the top times the bottom minus the derivative of the bottom. What's the derivative of the bottom with respect to X? 2x times the top. All over what? Bottom squared. Then subtract from that the partial of P with respect to Y. So what's the derivative of P with respect to Y? So quotient rule again. Derivative of the top is what? -1 times the bottom. X squared plus Y squared. And then What do we got? So what is the derivative of bottom? 2y, and then times the top, minus y, and then all over the bottom squared. Yes? And then dA. What does this turn out to be? So let's look at this top numerator up here. What's this really going to turn out to be right here? X squared plus y squared minus 2x squared, so y squared minus x squared, right? They both have the same denominator. So I'm going to put them together. What about this? What does this turn out to be? And I'll put the subtraction here. So that's this. So what does this turn out to be? Negative x squared minus y squared, then plus 2y squared. So that's what? Y squared plus x squared? Negative x squared, sorry, in front. Thank you. So what do we get? And then we subtract that, right? So subtract y squared minus x squared all over x squared plus y squared squared dA. So what do you get on top? 0, and on the bottom doesn't matter, right? So you get 0. Double integral over d of 0 dA, which is just 0. Now, that doesn't answer the question, because what was it that we were trying to find? We were trying to find this, right? And show that it's 2 pi, right? That's what we were trying to figure out. And what we just said was this right here equals what? Equals 0, right? So what we have is that this integral f dr minus this integral c prime f dr is equal to 0. So what can you tell me about the two of them? The line integral over c and c prime are the same, right? Move that to the other side. They're equal, aren't they? Now, why is that a good thing? What about this line integral? C prime was that little circle, right? The little arbitrary circle I made? And I can figure out what that is, right? That's right. I've turned it out. I've basically reduced any path that encloses the origin to the path of a circle radius A. Now, that only happens because we got 0 here, right? Had this not been 0, this wouldn't work. So we're not done, but here's what we can conclude now. Therefore, line integral over c of f dr is equal to line integral over c prime f dr. So now what we're going to do is we're going to go figure out what this line integral is. That's what we're going to do. Questions so far? Okay, so I'm trying to find this line integral over c prime f dot dr, where my c prime looked like this. C prime was positive orientation, wasn't it? Okay, so I have the parametrics and stuff for that. What kind of region is that? Well, I guess my question is, do we want to do this as a line integral, or do we want to use a double integral? What do you think about a double integral in Green's theorem? Okay, so so our new little d is this, right? All that. So my theta goes from 0 to pi, right? My r goes from what to what? 0 to a. What's that? Well, remember, this is going to be the double integral over d of what, though? Not of 1. Of partial, yeah, we got to do all that stuff. Partial q with respect to x, right, minus partial p with respect to y. Didn't we find those a little while ago, though? Didn't we do that right here? Yes or no? Hold on a second. No, hold on a second. Well, that's what we're going to try and do, but are we going to get the same answer? We can get 0 again. Yeah. Let's do this. Hold on a second. Let's do this. Damn it. Okay. Let's do this. What would that vector function be? A cosine t, a sine t? Okay. What would dr be? What's the derivative of this? Negative a sine t, a cosine t. Now, the way that this works as a line integral, t goes from 0 to pi, right? The way that this works as a line integral is that, so I'm not going to a double integral. I'm sticking to line integral. We need to dot f with dr, right? Which is f evaluated at r of t dotted with r prime t dt. So what is our function f, which is the vector field, evaluated at r of t, which means evaluated at these two? Wouldn't that be, it was negative y, so negative a sine t over what? X squared plus y squared? What's x squared plus y squared? A squared? And then on this one will be x over a squared, so x is a cosine t over a squared, and then we're going to dot that with negative a sine t, a cosine t, dt, which is integral 0 to pi. What happens when we dot these? This times this would give us a squared sine squared t over a squared, which would just give us sine squared t. And then we do this one, we get what? Plus cosine squared t dt. And that's just 1, isn't it? 0 to pi dt, which is t, 0 to pi, which is 2 pi. Do you all follow that? Now, my question to myself here is why we were going to do double integral up here. Why would that have not worked? Or would it have? Oh, I know why. Oh, no. No, hold on. F, where's P? Let me think about that. Let me think about that. I'm having a brain fart up here. This right here. Why not have just used that when we got there? Yeah, but it shouldn't. I mean, we should get 2 pi, right? We did use it, though. What we did earlier was right. This part right here, this was correct. This is okay. Let me think about it. This is P and Q. If this is our function, right? Our P and our Q, then when we got to here, right here, our P and our Q would have been the same. No, because we didn't need it to be conservative here for this to work. Let me think about it, everyone, okay? Yes, but then our answer here should have been 0, right? When we do our double integral conversion, we have to do the partial of q with respect to x minus partial of p with respect to y, right? That's what this tells us, right? I'm going to have to think about it, and right now my brain doesn't want to think about it. All right? I don't know. I'm having like a brain fart moment, and I just don't want to continue to have brain fart moment up here. So I'd rather we move to 13.5. All right, let me make sure all my stuff is ready. My Mathematica code for this section usually requires every resource of my computer to make it work. So, all right, we have somewhat of a different topic now. We're going to just briefly step away from line integrals and things like that to talk about 2 important vector field operations. They are called curl and divergence. So given a vector field F, we now define 2 operations on the field. The curl of F will result in a vector. The divergence of F will result in a scalar. So remember when we had 2 vectors, we could do dot product and cross product. Well, when we have a vector field, a single vector field, we can define what's called the curl of the field and the divergence of the field. So here's what the curl is. If F is equal to PQR and the partial derivatives exist, then the curl of F is defined to be this vector. Partial R with respect to Y minus partial Q with respect to Z, blah, 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 blah. I won't go through the rest of it. It's all there. But another way to remember it in an easier way is to compute a cross product to get the curl. So y'all remember how to cross 2 vectors? we made this table up, and then we wanted to cross it to get the I. We covered up I, and then we did the determinant. Then covered up J, did determinant, and then reversed the answer, and so on and so forth. Well, the curl of F is defined to be this right here, which is del. Del is what we call a partial operator. Okay, so what's going to happen is we're going to take this, we're going to cross it with F. Del by itself doesn't make any sense, right? Del is not a vector, it's just del, all right? What we are going to look at as del as being is a vector of operators. So del is the vector, the I, J, and K components are the partial with respect to X, partial with respect to Y, partial with respect to Z. So when I take the del and cross it with F, when I want to figure out the I component, I do the determinant here, but it's not multiplication, it's an operation. Look, it's the partial of partial with respect to Y of R. Or in other words, take the partial of R with respect to Y. Understand? That's not multiplied. Looks like multiplication, but it's actually taking a derivative. And then minus the partial with respect to Z of Q, or the partial of Q with respect to Z. Do y'all see that? Then cover up J, go across, and then change the signs, which flips the order. What? Well, because if I ask you to multiply 4 times 8, it makes sense, right? But I'm not asking, we're not multiplying, right? Differentiation is not an operation like multiplication is. We're treating it like it's a multiplication, but it's not. We are taking visually it is, but we're actually taking the derivative of R with respect to X, aren't we? We're not multiplying the two. So as long as you understand that del by itself as a vector makes no sense. Like if I say, hey, you know what? If I give you PQR, could you graph it as a vector? Like if I gave you the actual values of PQR, you could, right? But I can't give you a value of del, and you can see it. It's an operator. But in that notation, it's easy to remember the formula, right? If you write it in that notation. So, I said it right here. This del right here, defined to be this, is called a differential operator. Did I forget to change the sign? You go this, right? That should be positive, and then you subtract this, right? But then switch the sign because it's the J component, which makes this one negative, and makes the one that was this way, which was negative, now positive. Do you see that? You're okay? In my mind, I was thinking you had to like do the differential of R minus the differential of C and then change the sign. It'd be the same thing because it's a constant, and constants with differentiation, constants can come out and it won't matter. All right. So let's find the curl of this, and then the magnitude of the curl at a point. So this is very much just computational stuff. There's not anything you have to sit there and think about what does that look like, or you know what I'm saying? What's the shadow of that? This is just purely computational. So we have F is defined to be x squared yz, xy squared z, xyz squared. And then we're trying to find the curl. So to find the curl of F, it's going to be del crossed with F, which is going to be I, J, K, del, so partial with respect to X, partial with respect to Y, partial with respect to Z, and then x squared yz, xy squared z, xyz squared. So let's go ahead and do this. The I component will be the partial with respect to y of this piece, which is just what? Xz squared minus the partial here with respect to z of this, which is xy squared. Okay, that's the first part. Now we do the next one, right? I won't draw any more circles. Let's just do it in our heads. So what's the partial with respect to x of this one right here? Yz squared, but then we're going to subtract it, right? So minus yz squared, and then partial z with respect to partial with respect to z of this x squared y. That was minus, but now it's plus. And then finally, the kth component, or the k component, is going to be partial with respect to x of this y squared z minus partial with respect to y of this x squared z. Understand? So that's the curl, right? And now find the curl and the magnitude of the curl at a specific point. So at the point 210, the curl of f is equal to what? So plugging in 2 for x, 1 for y, and 0 for z. I think we get negative 2, let's see here, 4, and 0. Replacing x, y, and z with 2, 1, and 0 respectively here should give you negative 2, 4, 0. That's the curl. It's a vector, right? The curl is a vector. And now the magnitude of the curl is the square root of what? Root 20? Right? 4 plus 16, square root. That's pretty straightforward, isn't it? I mean, as far as computations are concerned, not a whole lot going on there. All right, now let's look at another one. Find the curl of the vector field f of xy equals 0, negative x squared, and then find the magnitude of the curl. Well, what's the problem here? What's the issue? It's two-dimensional, right? Two-dimensional vector field. The curl requires us to compute the cross product. The cross product is on vectors in 3D only, right? So all we're going to do, and we talked about this at the beginning of class, is whenever you're going to try and cross a vector that's two-dimensional, you just extend it to 3 dimensions. So we add a third component to this. So what we'll do is we'll redefine capital F to be the vector 0, negative x squared, 0. So now we've extended it to 3 dimensions. So you just always throw a third component of 0 on there. And now let's compute the curl. This curl should come out pretty nice. Del should get lots of zeros here, right? What do you have here? The ith component is what? 0. The jth component, 0. Right? Cover this up and go across there. The kth component is going to be the only action here. What do we get? Minus 2x? Is that it? So that's the curl, right? Now in this problem, it doesn't give me a point to compute the curl at. It just says find the actual magnitude of the curl. So the magnitude of the curl in this case is what? The square root of negative 2x squared. So just 2x. Questions? Now for the fun stuff. Let's try and understand what curl is geometrically. We have a vector field, right? Just give this thing a second. Okay, we have a vector field, right? Three-dimensional vector field. If I'm standing somewhere in that vector field, let's say this is like wind or something, right? If I'm standing there, at every point there's a vector that describes the direction at which and the strength of the wind at that point, right? So it's if I'm standing at some point, there's a vector that says, oh, you should be blowing in this direction with a certain velocity, right? Certain speed. Yes? That's not what curl is. Curl is not that. Okay, curl is this. I'm going to take the vector field out of here. I got to kind of turn this. All right, can we pull those? I want you all to be able to see this. It's kind of hard. Can you just draw that one down? There's some subtleties here. Okay, so if I'm standing at this point, okay, it's this point right here, okay? The red line is the vector field direction. Okay, so I want to go in this direction, or it could be the other way, but let's just say for the sake of this, it's that direction, okay? Got it? That's what's happening there. Now, if I turn this, you see that's like a disc that I have around it. If I come up from the side, you can just barely see the disc, right? Okay. So what I'm going to do now is start playing this. Okay, you see that disc? I have the black line on the disc so you can see it turning, right? So what's happening is I'm at this point and I'm headed in that direction, but if I was like a ball, there's wind around me, right? There's all sorts of shit happening all around me. And so the curl is actually describing which way and how fast I would actually be rotating as I was going that direction. So the curl of the vector field. So even though I want to go in the direction of the red line, I actually have some sort of curl or twist to me as I want to go. Does that make sense? If your curl is 0, then you don't. You're just going in that direction. But if you have curl, then it wants to turn you as you go. Yes? The what? What you're doing is you're taking into account what's happening around you. And not only, you already know that you want to go in a certain direction with a certain speed, but you're also taking into account the stuff that's happening all around you and how that might be twisting you. Now, you only have to look at it in the plane of the wheel. You don't look at it tilted or anything. Just, I'm going in that direction, so am I wanting to turn or not? Make sense? Now, the way I've written this code is that time is the same for every point in this three-dimensional space. So if I move this point in three-dimensional space, I might have a different curl. So right now, what's my curl? This right here is a vector, right? And then the magnitude of that vector is 3.2. Y'all with me? I'm going to move the point now, and let's see what happens. Smaller curl, right? Can you tell? Well, you can't tell if you're looking at it from that side. There we go. Can y'all tell it's turning slower there? Okay. So I have less curl happening at that point. Oh. Now it just turned red. No, it didn't. My curl is always going to be positive, right? So, got it? Understand? It's a twisting motion. Now that's a three-dimensional vector field. And I tell you what, for those computer science people, this is one of the hardest things I've ever had to code in Mathematica. The hardest part of it is getting, okay, as you might imagine, is getting the computer to draw a circle. I'm sorry, turn this off. Forgot to turn it off. Is to draw a circle. Come on. Right, to draw a circle in arbitrary space. I mean, everyone can draw a circle that's parallel to a coordinate plane or something, but to just draw an arbitrary circle, twist it around, that's not as easy. That takes some transformation stuff that was pretty hard. But needless to say, it was done. Now, the two-dimensional vector field, you can still compute the curl, right? We said we extend it to 3 dimensions. The two-dimensional one is easier to visualize. Let me get back to this one, make sure this one's turned off. Okay. Let me pause this one. Let me start this over. This was the first example. This was the first example I gave us. The vector field was 0, negative x squared, right? We extended that out into 3-dimensional space. We said the curl would be what? 2x. The magnitude of the curl was 2x. And if you look at what we had gotten, the curl vector, look at the curl vector. 0, 0, negative 2x. Which way is that pointing? If this is like the xy plane, the curl vector is pointed out towards us, right? Curl is pointed towards us. So imagine, or into the paper, it doesn't matter. Imagine that point, instead of it being a point, is a little like point with little paddle wheels on it, right? And this is like flow of liquid. Then right now, what's going to happen if I'm at the origin from this pattern? You're going to have flow pushing on this side, right? Pushing these paddles down, pushing these paddles down, and what should happen? It shouldn't rotate at all, right? Because it's equally pushing on both my paddles. Now, if I move this way, what's going to happen? The bigger vectors mean stronger force, right? So what's going to happen is it's going to start rotating clockwise as I move to the right. So if I move it to the right, see? It's moving, rotating this way. If I move it a little more to the right, it's going to move faster. It's actually moving so fast now, it looks like it's just like flashing almost. But you can see what the curl is here, all right? Now, I have negative curl because the rotation is clockwise. If it rotates the other way, it would be positive curl. So let me move that over here. That makes sense? You change the vector field. Let me take us back to the origin. Here's another vector field, just a completely different one. So what should happen if I move left or right here? Left or right? Think it'll change? Think it'll start rotating? What if I bring it this way? Don't these look equally as powerful, right? Pushing on both sides so nothing should turn? see, if I move it down here, nothing happens. So I'm getting no rotation about that point. In fact, it looks like no matter where I am in this vector field, it appears that I would get no rotation. If it stays black, it's not rotating, and my curl is 0. So no matter where I am in this vector field, the curl is 0. Got it? So the curl vector creates an axis of rotation. I need to go back and kind of explain something here, because I think I may have confused you. Bring you back to this picture. This red vector, I said was the field, was the vector field vector, didn't I? This red vector is not the vector field. Here's our point, right? We have a vector pointing somewhere for the vector field. What happened? Okay. There's our vector field, all right? So this is F. This vector here I said was F, didn't I? That's the curl of F. And then you have the rotation. So I need to completely restate that. If I'm in three-dimensional space, if I'm moving in that direction, let's say, right? I'm a point. I'm moving in that direction because of the vector field. But as I'm moving, there's another vector, okay, which is the curl, and I'm wanting to rotate about that curl, about that axis of rotation. I'm wanting to turn as I go in that direction. Make sense? Now in 2D, it doesn't matter because your curl vector is always sticking out of the page. It's always going to be sticking out. And so you're always turning this way or this way. So it's always rotation like on the plane. The sign. Okay. Let's proceed. So the curl vector creates an axis of rotation, and the magnitude of the curl gives us the speed of the rotation about the point. This is important because of your take-home test. If the vector field represents a velocity field of a flowing fluid, then curl measures the tendency of the fluid to rotate or curl at given points in the fluid. If your curl is 0, then there is no rotation, and the field is called irrotational. So I gave you that example where I moved that thing around and nothing happened. That's because the curl was 0. So I will say for your take-home test that the way that I want you to look at irrotational is that you could say that the entire vector field is irrotational. That means its curl is 0 everywhere. Or you could say that there are certain places within the vector field where there is no rotation. So that maybe if I move around, maybe here I'm rotating, right? But if I move somewhere else, I'm not. I think on your take-home, I ask you to find the points in a vector field where you're irrotational. Is that what it says? Something like that? Okay. And then this is just, remember, we can extend a two-dimensional vector field into 3 by adding a 0. Now, here's a nice result. Remember what it took to check if something was a conservative vector field before? Conservative? We did the partials and saw if those two partial things were equal to each other, but we said that only worked if your vector field was what? Two-dimensional, right? This is the big result now. We saw here that if these two partials are the same, that only worked in R2. We now establish what we need for a vector field in R3. This is beautiful. Look at it. So simple. If the curl is 0, it's conservative. If your curl is 0, it's conservative. But it would have to be conservative everywhere. I mean, like, It would have to be curl 0 on the entire field. Then it's a conservative vector field. Now, let's look at that compared to divergence. Divergence. If F is PQR and the partials exist, then the divergence of F, which is a number, and the answer comes out to be a number, is defined to be, this is probably the easiest computation in all of Cal 3 ever. All right? Out of everything we've done, this is probably the easiest computation that you've ever had to do. You're given a vector field PQR, right? You take P, differentiate it with respect to X, add to that Q with respect to Y, add to that R with respect to Z, you're done. All right? No crosses, no dots, nothing. Just straight up partial derivatives, X, Y, Z in that order, left to right, done. All right? Another way to look at it is del dotted with F. Del dotted with F. Would you agree with that? Del dotted with F? Okay. All right, we won't even write this down. Let's just talk through it. What's the divergence of this thing? What's div F? Div F. 2xyz plus 2xyz plus 2xyz, which is 6xyz. All right, the divergence is 6xyz. All right? Now, what's the divergence at 2, 1, 0? 0. Right? How many of you have seen curl before? Like you've heard of it, seen it? No? Curl? Divergence? Have you ever seen visual representation of it? Yes? Okay. Have you seen visual of divergence? Yeah? See if I can try and help you see this visually. If the vector field represents, so again, we have a vector field. Let's say it's velocity, a velocity vector field of a flowing fluid. Then divergence measures the tendency of the fluid to diverge or leave a point in the fluid. I'm going to show you this geometrically in a second. So if we're given a point in three-dimensional space, if the div at that point is bigger than 0, so you have positive div, then the region around the point is called a source. If the div is less than 0, then the region around the point is called a sink. If the div is 0, then the region around the point is called incompressible. So it's, let me show you the example, or the illustration. There's my vector field, right? So what I'm going to try and get you to see here is that we have three-dimensional space, right? In three-dimensional space, we have a point, right? A point. At that point, we have a vector coming off of that point, which is the vector field itself, yes? Associated to a point inside that little sphere is a vector coming off of it. And we could compute the curl there and everything else, right? Now, div, what div looks at is not a point, but an infinitesimally small ball around the point. So imagine taking that point and just blowing it up into a little infinitesimal ball, or sphere, I should say, okay? And then looking at all the points on that infinitesimal sphere and looking at the vectors from the vector field on that sphere. So here is, if I take, what you can't see here is, I've taken this infinitesimal ball and I've picked just a bunch of points all on the outside of that ball, okay? And at one of those points, I had a vector from the vector field. From the vector field, it was pointing off like that, okay? And there was another one I picked, and it's way up here like this. Got it? All the ones in green are the vectors coming out of the ball. All the ones in red are the vectors going into the ball. Got it? Well, if I have a ball, right, and I pick a point on that ball, I could have a vector pointing in any direction, right? If that vector comes out of the ball, it's green. If that vector punches through, and it might come out the other side, but if it punches through and goes inside the ball, then I'm looking at it as red. If I take those and I add up and I say, do I have more green or more red? That's your divergence. In this particular case, I hope it's obvious from the picture that you have more green than red. So you have positive divergence at this point, right? Now, I could throw more and more vectors in there to convince you, right? More vectors, that's overwhelming green. Or I could take out, just show you a few. But if I show you a few, you may not be convinced. Let me zoom in on that ball. And let me actually take the ball out of here a little bit. And I can make the ball smaller. There we go. See it? So this would be positive div. So you would call the region around this a what? A source. It's like if you're looking around that ball, there's more coming out than going in, right? Things are moving away from that ball more than they're moving in. So it's a source point. Got it? Move it around. Let me see if I can get some negative div here. There we go. So I actually move that ball around in the three-dimensional space. And you can see now I've got more red than green. Now in 2D, it's the same thing. Right now, if I zoom in, my div is 0. Why is my div 0 there? I have as many vectors going in as the ones coming out, right? So that would be a what? That region around that point would be called what? Incompressible. Incompressible. Now if I move it, let's see, I'll move it to the right a little bit. Look at that, my div is still 0. Look, you've got bigger ones coming in the right side, don't you? But you have bigger ones leaving the right side, and they're all just equaling each other out, right? So my div is always 0. What if I move up? If I move up, shouldn't matter, should it? Up or down? Nothing's changing. My div's always 0 on this. Isn't it? Why is the div 0? What's the computation of div on this? First, we have to extend it to 3 dimensions. So it's 0, negative x squared, 0, right? Then take the div. Partial of this with respect to x. 0 partial of this with respect to y. Partial of this with respect to z. 0. So you get 0 plus 0 plus 0. So your div is always 0. Now, if you do something more interesting, like maybe this, different vector field, now you're getting some div, right? And the div depends on where you are. So we have, now that we've defined what curl is, we have a different way of defining the Green's theorem we just had. We have the line integral over C of f dot dr is equal to the double integral of curl of f dot k. What the heck's that? What's the curl of f? Let me go back to what the curl of f is. Well, in Green's theorem, sorry, I should say this. In Green's theorem, what was this supposed to be? Forget this part right here. That right there. What's it supposed to be in Green's theorem? Partial q with respect to x plus partial p with respect to y, right? And I'm saying it's the curl dotted with k. What's the k? What's k? What is k? It's the z direction, so it's the vector 0, 0, 1, right? 0, 0, 1. So I'm dotting the vector 0, 0, 1 with the curl. What was curl? Curl is that big ugly formula, right? But look at the last component. What's the last component? Partial q with respect to x minus partial p with respect to y, right? So if I take this curl vector and I dot it with 0, 0, 1, the only thing that survives that dotting is what? That last piece, right? Yes? So all this is piece is the that partial piece. So it's just another way of writing it, right? Another way of writing something we've seen. And then also, we can rewrite another version of Green's theorem. Now this is different because it's not f dot dr, it's f dot nds. Look back in your notes when I went over that. But this, when you dot these two, it's this right here, the div part, the div of f is just the sum of the partials, isn't it? The sum of the partials, so sum of, what is it? P with respect to x, q with respect to y, z with respect to, r with respect to z, sorry. All right, identities with curl and div. There are many relationships, identities involving curl and divergence. The next example shows how you might be able to prove an identity. All right, so or an identity and how to prove it. So, is that printout in there or no? Does it have the actual work there? No? Okay, good. Because I don't want you to. So here's what I want to try and show. The div of f cross g is equal to g dot curl f minus f dot curl g. Show this. So how do we show, how do we prove identities? Like how do we do it like in pre-cal and things like that? How do you show something is always true? Start with one side and turn it into the other, right? Start with one side, turn it into the other. So I'm going to start with, well, what do you want to start with? Left side? All right, so how do you want to do that? Okay, so we're going to start with the left side here, and we're going to try and turn it into the right side. So I want the div of, what's the cross of f and g? Well, hold on a second. There's so many different ways of doing this that we're all going to find our own path to the answer here, hopefully. And this is one of your take-home problems, right? On your mini exam, the last problem is to show an identity. All right, I'm going to start by just rewriting what is the definition of div. Div is the del dotted with f cross g. Do you agree with that? Now for this example, I'm going to have to define over here f. F is PQR. I'm going to call it P1, Q1, R1. And then G is going to be P2, Q2, R2. So F and G are two vector fields. They have components P1, Q1, R1, and P2, Q2, R2 respectively. If I want to take the div of that, then I'm going to need to dot del, right, with F cross G. So shall we find F cross G? Dot del with, what's F cross G? It's a vector, isn't it? What is the vector? Can we do it from this right here? Okay. So it should be P1 times, no, Q1 times R2 minus Q2 times R1, or R1 times Q2. And then I keep going. Now I need the J component. So P1 times R2, but then I'm going to switch it. R1 times P2, but switch it. So R1 P2 minus P1 R2. Following me? And then my last one, P1 Q2 minus Q1 P2. Now del is a differential operator, right? I'm going to dot it with this. I realize we don't want to rewrite all this, but what is, can I just erase this and put what del was in front here? Okay, what was del? What's del? Uh-oh. Dotting. It's partial with respect to x, partial with respect to y, partial with respect to z. Okay, when we dot, we just do component by component, right? Here to here, here to here, here to here. Let's talk about that first, the first one, okay? This one right here. What do we get here? So I'm going to put it in parentheses so we can just keep it together. I'm going to do the partial with respect to x of Q1 R2 minus R1 Q2 the what? Where are you talking about? Yes. P1 and P2, yes. Whoa. Okay, hold on. You've thrown. I thought I had a mistake. I haven't taken the partial yet. I'm just writing down what it is. This times this, all right, really means the partial with respect to x of this, right? That's what it means. So just hang tight. I haven't taken a partial yet, all right? Plus partial with respect to y. Now I'm doing this one. Partial with respect to y of what? R1 P2 minus P1 R2. And then finally, partial with respect to z of what? P1 Q2 minus Q1 P2. Now, I think what you were saying is that this should be 0. Yeah, see, we don't know if Q and R contain X at all. So we have to figure it out. Now, this is the trickiest part of the whole thing, I think. Because again, this is not multiplication. This is actually differential operation. You're trying to take the derivative of two terms, right? Can I do term-by-term differentiation? So can I take derivative of this one separately? Yes? Now, when I take derivative of this one, what will I have to do? Product rule. I will have to apply a product rule to this. That's the tricky part. So let me just keep writing here. This is going to be partial with respect to x of Q1 R2 minus partial with respect to x of R1 Q2 plus, and then all that junk over there, the same thing, distributed through, right? Distribute all that through. Distribute the operator through. I have not taken derivative yet, right? I've just applied the derivative to each of these terms. Now, what is the derivative now of this first piece only? I'm just talking about this guy right here. What's derivative of that with respect to x? It's the partial of Q1 with respect to x times R2 plus the partial of R2 with respect to x times Q1. That is the blue part. That's it. That's that one derivative, right? Product rule. Derivative of this one times this plus derivative of this times this. Or there's different ways you can have product rule. But when I say derivative of Q1, I mean the partial derivative of Q1 with respect to x, then times this one, then plus partial of Q1, or sorry, R2 with respect to x, then times Q1. And you've got to do that for this one, right? With minuses distributed. Then that was just this, right? And then you got to come and do these all the way down. Okay? Now, where are we trying to get with this? So I think what I'll do is I'll bring up the solution now so you can see how this would work. Okay, so here's where we were. We just did this one, right? Their order is backwards from mine. I did partial Q1 with respect to x times R2, right? Plus partial R2 with respect to x of Q1. I did that, right? Then you have to do the rest. These are the next two that would come out, and that would have taken care of just that first group, partial with respect to x. So there would be 1, 2, 3, 4 terms for that first one, right? Then for the next one, which is the partial with respect to y being distributed through, you would have 1, 2, 3, 4 terms there. Then you do the partial with respect to z, which would be these 4 terms here. So this is all one line. Do y'all see that? Now, if you look at these and collect all like terms, you'll notice the things that have P2s in them, right? P2s. So where do I have P2? Just P2, not derivative. There's a P2 right there, right? And then here's a P2. If I take that, right, where was it? P2 here? And P2 here. Take that P2 out, I get this factored out. When I factor out, this is what I'm left with. When I take Q2 out, I get this. When I take R2 out, I get this. Yes? So this is P2, Q2, R2. Isn't P2, Q2, R2, isn't that G? Isn't that G? And then when I factor out R1, or P1, PQ, R1 from that, I get these. And what you'll notice is that this part right here, this partial thing, is curl of F. And then the things in front of it are G. So that's G dotted with the curl of F. And then these partials right here together, that's curl of G, and the stuff in front of it is F. So it's a lot to have to try and extrapolate, but that's the way it's done. Does that kind of make sense? So that your take home will be the same way. Why is there a minus here? Ours wouldn't have had a minus because we switched the order, didn't we? Did we? Yes, we had switched the order, so it wouldn't have mattered for us. But you'll have to really make sure you keep track of all the signs in this thing. So on your take home, you're trying to show what on your take home? Something. Bless you, I think. I don't even think I have this one written down. Here's my final from last semester. Okay, yeah, what is it asking me here? Yeah, oh, okay, let me grab this, can I? Is it all stapled? The one you're being asked on your take-home is very different than, well, not very different, but somewhat different than what I just did. You're being asked to show that the curl of f equals f curl f plus del f, or gradient of f, cross f. Now, look, when you turn this in, is this due Wednesday? When you turn that in Wednesday, or when you don't turn it in Wednesday, I don't know what you're going to do. But if you do this problem and turn it in Wednesday, give me your final cleaned up version. Don't give me your, I was working through this but had to erase this five times and redo it version. I just want the nice, clean, let me follow step by step, right? When you're trying to prove an identity, we all know it's true, right? So I'm not looking to say, oh, look, they started here and they ended with the identity. Great, good job. I need to be able to see the work, like how you did it, make sure it all flows. So it can't be this just chicken scratch that I can't make sense out of. So nice and neat final version turned in, please. I wanted to just point out here, f is what? A scalar function, right? A scalar function. Capital F here is a vector field. So you're basically saying that if you have the curl of a scalar function times a vector field, that, what does it almost look like? What does that almost look like? Come on, who can pick up on that? It's almost like a product rule, isn't it? I mean, it's kind of like, what's the derivative of a product in here? Well, what's the derivative of f? It's like curl derivative, right? Almost. But it's f is left alone. Something happens to the vector field. This one, something happens to the f, and then you cross it with the vector field. So what have you ever learned in the past that if you're ever trying to prove an identity that's hard, that when you start on one end and you can't make it turn into the other side, to do what? Go to the other side and work that one down and try and meet in the middle? If you do that, that's acceptable to me. Just make sure you write down, left-hand side, work it down, getting to a stop point, box it, then do your right-hand side, work it down, get it to a point, box it. They're equal to each other. That means you just follow it back up and you're back to where you started. So just make sure you're operating with each side separately, right? See how that goes. Yes. I think it is. Yeah, this is what, number 5 or 6? 5, yeah. You want another one, Evan? 3 more? Well, we only have next week we stop, right? I mean, we're pretty much there. This one's due on Wednesday. Next week we just have to finish up 13, right? Chapter 13 we'll finish up by next Monday, and then Wednesday we take the final. So not a whole lot of time left to send you home with anything. You've done pretty much what I do in a normal semester for take-homes, because when we get to the end of chapter 13, there's not a whole lot of time left for you to be able to go home with anything. So normally, a traditional semester we do 8 take-homes, which is 1 every 2 weeks. You've done 5, which is for an 8-week semester. That's a little more than 1 every 2 weeks. So, but you've done most of the problems that they would do. Like some of your exams were longer than theirs were. Okay. 13.5. I think I'm done with 13.5. Check that. Let me check this. In 13.4, there was a homework assignment for 13.4, wasn't there? Let me double check the 13.4. 13.4, 1 through 13. Okay, this is a good homework assignment. The only problem is it's page 780. Oh, it is right, 787. That is correct. That's, oh, yours says 765? Well, it's supposed to be 787. That's from 13.4. Yep, that's 13. I jumped back, sorry, because I want to make sure I gave you. So that's from 13.4. I'm checking 13.5 right now. Hold on. Page 765. That can't be right. Can it? Go backwards. 11 through 15. This is correct, but at wrong page number. 795. Those are correct. I know y'all are all packing up. Where y'all going? I thought we have 20 minutes left. 2 more days, finish 3 sections? It's, yeah, the next section's one of the longest, though. It's, well, let me see what it looks like. Everyone have that down? Well, your homework, and then did I give you all a copy of, before last exam, did I give you all my midterm from last time? I did? I think I'll probably do the same for the final. I'll show you what I gave them last semester for the final. It was only, no, it only covered everything after the midterm. Mm-hmm. No. Yours is. Nobody else's is.
Oh, I'd actually prefer that.
Probably, right? Sometimes that's a good thing. Let me see. Let me take a look at my final. So look, I'm breezing through this real quick just to show you kind of what the final was. They had double integral over a pretty clean region there. Triple integral. Spherical coordinates. Line integral of a scalar function with respect to arc length. Work. Find potential function. Then compute your work using the fundamental theorem of line integrals. Green's theorem. What we haven't done. 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 Well, everyone's ready to jump out of here. That's why I'm saying, like, you want to look at the final, or we only have 3 days. There's a lot of stuff. It's heavy loaded in the end. Mm-mm. Mm-mm. No. No, there's no 11.8 because I don't want to grade it. No. Okay, so look, you have no choice, but we're going to talk. We're going to talk for. Well, shoot, we have. Let's talk. It was good. It's not good anymore. Okay, no. Here's the thing. We can wrap it up, but here's what I want. Just make sure you understand the next class, the next two classes are going to be very important. That we push as hard as we can. The most difficult part of this is that we need to come up with another way of drawing surfaces. And so that takes a little while to establish first. Once we understand that, then we can get to how we're going to use it. But imagine this. What we had before, with today, what we had was this. We had that if you had a curve going around a region, then you could turn this line integral, right, into a double integral, right? So what we're going to do now is we're going to try and take some sort of like, well, we won't do something that complicated yet, but let's take a sphere, and we want to do an integral over its surface. So we want to integrate over the surface. Then eventually what we're going to realize is that we can convert this surface integral into, guess what? A triple integral, and look at the solid inside instead. That's where we're headed. But we have to first understand how can we draw a surface in other ways. So we're going to look at parametric surfaces, and that'll be a lot of next class. And then we go from there. All right? So you'll just be ready to roll the next 2 days we're in here. And you can go, 4:15. Okay?